Just the quick introduction. Ryan is getting close to finishing his PhD, so we're going to hear some of the interesting results that he has been working on.
Ryan, turn your camera on so we can see you.
You can. Most of us have the ability to do that. There we are.
Okay. All right. Guess get started now. So this presentation's over some of the work I've done looking at the drill sites that the Curiosity Rover is capable of drilling on Mars. So I don't really look too much at the sample itself that's taken up and given to the internal instruments. But I look at the surface around there, the drill finds produced by the drilling process, as well as the drill hole itself. And we're using the ChemCam instrument to get geochemistry data on all of that. All right, so like I said, this is going to at first provide an overview of the ChemCam analyses at each site. And this is for the each site drilled before the drill fault. So the process the process of the drill fault and the specifics of the materials it produced were all very well reported on by the engineering team before this drill fault happened, but then they changed the drilling process. So instead of trying to maybe compare apples and oranges or delving into a new process, I kind of ended what I was looking at that point. It also provided kind of a organic break to allow me to focus more on the sites themselves than just continually cataloging these sites. So like I said, going to use ChemCam data on the rock surface, the drill hole wall, the drill tailings, and the dump piles. And originally the purpose of this research was to characterize these drill sites as completely as possible. And the thing that made this really exciting is that the drill tailings, which are produced at the first part of the drilling process, come from a distinct portion of the hole than the dump pile, which is the material collected by the drilling system. So here I have a little cartoon on the anatomy of a drill site. So the drill site's about 6.5 centimeters deep. You get some powder material that falls back in. And so what's interesting is the drill, when it originally came in, had a collection tube. And that tube wouldn't connect, wouldn't bite into the surface until after it had already drilled about 2 centimeters deep into the surface. And it would push out material that we call the drill tailings that all or mostly came from this location. Then the drill bit would bite into the surface, and the drill would continue down up to 4.5 centimeters more and collect some material. This material was sieved, processed, prepared for the internal instruments, which includes an X-ray diffraction instrument. And then some of this material is dumped back onto the surface in this thing we call the dump pile. And so we can compare these two materials to get an idea of differences down the drill hole. We also, with ChemCam, have sampled the very surface of the drill hole, as well as we're often able to shoot into the drill hole itself and sample down the drill hole. Not down the, it's only down a little over 1 centimeter typically. And so it doesn't give us the full range. And then if there's any kind of like diagenetic materials like calcium sulfate vein, we may not get a characteristic sample, which the drill tailings has the opportunity to provide. So I wanted to do some house cleaning first, because I'm going to talk about a few things, and if we don't talk about them now, some things may not make sense a little bit later on. So the ChemCam instrument uses laser-induced breakdown spectroscopy, which is a very energetic process, and it can blast away loose material in only a few shots. And the drill finds are, of course, loose material, and not a lot of loose material. It's not like shooting into a soil where there's just a lot more soil underneath it. So we know. So based off of previous research by the Curiosity engineering team, we know the drill fine should be a fairly well mixed and homogeneous material. So the ChemCam shots into them need to reflect that. So what I did was I first investigated some of these drill finds at the most homogeneous drill sites, and we'll talk about that part a little bit later on. And so for this research, I compared calcium and silica. Silica just is kind of a proxy for the silicates making up the whole, and then calcium, because it makes up calcium sulfates. It's a fairly bright material, and it seems to be the first thing, at least in my experience, to start contaminating the LIBS data. One important thing, if you don't know about ChemCam, that I forgot to say, it typically fires about 30 laser shots per point, and each laser shot has a unique spectra for it. So, all right, so if you look up at this top graph, what we have here are the we have the silica to calcium ratio on the y-axis, and then I ordered these various points into increasing silica weight percent to make a little more sense. And so the lines, this first blue line is just the first shot. Then you have the 3-shot average in this orange line. This gray line is the 5-shot average, and then this yellow line is the 10-shot average. And these colors continue down into this bottom graph, which is these same points, but it's just the silica versus calcium value. So if you want to see a little more raw, less processed version of the data, you can look here. But what's
so Ryan, so you're showing what happens when you when the ChemCam laser drills its way through the fines into the underlying bedrock. Is that the
yes? So
the example what you're showing here?
Yes. So the idea is to make sure we know about how many shots we have before we're probably penetrating the drill material. So so you don't really see the same changes in values in this when we're just using the first shot as we do with the subsequent shots. But you see with each subsequent laser shot, we get more and more material that's probably coming from underneath. Like I said, this is a fairly these sites should be fairly homogeneous. You shouldn't really have these big peaks in values here. So using the first shot would avoid most of this contamination from underneath the drill sites. Unfortunately, using the first shot could also mean we're sampling more airfall dust from Mars, or just windblown soil, and things like that that could bias our results. And so what we decided on using is this 3-shot average, because it does a decent job not collecting too much material if we're lucky and not right on the calcium sulfate vein. If the dump pile or the drill finds isn't right on the calcium sulfate vein, or really thin, the 3-shot average should provide a good opportunity to get the most amount of data with the least amount of contamination. And that's kind of unfortunately, it's kind of a balancing act here. The next bit of house cleaning is potassium anomaly. So some of the French researchers did some laboratory works and found that in some powdered material, potassium would be underreported compared to the original solid material. And so to see if we saw any of this on Mars, investigated drill sites without a lot of chemical variation at the sites. And we determined chemical variation based off of other people's reports. So this isn't like, oh, we don't see chemical variation here and there's no chemical variation, so there's no chemical variation. We're using kind of the more general results to understand this. And if you look over into potassium, you see at several points in this on this graph, which is the ratio of the drill tailings to the drill hole wall, which, if you remember, they're roughly the same part of the whole. So if you see several points where potassium is underrepresented, and kind of curiously, it seems to be this effect seems to be much stronger in these in the mudstones than in the sandstones. So we tested this in the laboratory. So there's a full engineering model of the ChemCam instrument at Los Alamos National Labs. And so luckily we had two standards that had already been powdered and sieved to different sizes. And so we were able to look at the changes in potassium at these different sieve levels to better understand what happened. And so the initial hypothesis and kind of the initial hope was that emission would change based off of the sieve size, and this was kind of based off of the mudstone seeming to have a larger anomaly than the sandstones. Unfortunately, there's not really a strong or much of a correlation with sieve sizes, and in addition, we were kind of hoping total emission might correlate at least somewhat with the change in potassium, and that's not the case either. So basically, originally we're hoping to create some type of simplistic correction for potassium to use, but that wasn't really the case. So in this paper, we're not really going to use potassium at these drill sites. We already gone fairly far into the research, and this hadn't been that big of a deal anyways. So just moving forward, we're just not going to present potassium, because you can't really compare the solid surface and drill hole wall to the powdered drill tailings and dump pile. So moving on, once again, anatomy of a drill site. This is just really important, so I wanted to show it a second time. And okay, so here are the drill sites we've investigated in this location. So the first two are near the landing site, John Klein and Cumberland. Then you got the Winjana site, which is the last drill site really on the floor of the crater before we started driving up Mount Sharp. And then you have a series of sites in what's called the Pahrump Hills, and then moving into Marias Pass and the Stimson location. We have four sites in the Stimson, which are actually pretty important. And then we have 4 more sites up the Murray into the Murray Buttes before the drill faulted. So this is just to show that even as we've been continuing uphill, we've been seeing, or up strata, we've been seeing mineral changes at each of these sites. And like I said, there is an X-ray diffraction instrument on board, and that's one of the 2 instruments that the drill tailing or the drill site sample is delivered to. I don't want to delve too much into this because it ended up not being that incredibly important, but just visually you can see that the mineralogy is changing as we're moving uphill. Okay, so like I said, ChemCam extensively sampled most of these sites with points on the surface, the drill hole wall, the drill tailings, and the dump piles. I checked every single point for accuracy. So sometimes you try to shoot into the dump pile, or really, that's a bad example. Sometimes you try to shoot into the drill tailings, and it's since the last image came down, the wind blew it a little bit, or just your aiming was a little off, and so you get a few points on the surface, or you try to shoot down the drill hole wall, and you're just a little too high on the first few shots, so you shoot into the tailings. So I made sure all the points were moved around to best represent where they're supposed to be. The points on the surface and the drill hole walls used basically just what's the standard data processing technique for data, which is using a composition derived from the average spectra of shots number 50 through 30. And so, or sorry, that's number 6 through 30. With the first 5 shots thrown away in order to avoid dust contamination, which can be fairly important on the surface. And then, like I said, the tailings and dump pile only use the first 3 shots in order to exclude as much of the underlying material as possible. And then we didn't use potassium. All right, so I want to do a bit of an overview through all these sites. So here we have the 3 sites on the crater floor, and then the 3 sites in Telegraph Peak. The data shown here in order to be able to show silica through sodium fairly well is the average for each data type normalized to the average composition at each site. And basically, we just do not see a lot of variation in these first 6 sites. One of the changes we do see over here in John Klein is a change in calcium from the tailings through the dump pile. I reported on this in a previous paper. Basically, this maps up very well with just a change in the distribution, just by happenstance, a change in the distribution of calcium sulfate veins down the drill hole. But it does show that we're able to observe some of these differences. We do see this in Telegraph Peak, this large standard deviation in the calcium for here on the drill hole. So the drill hole wall. This is because there was a prominent calcium sulfate vein at Telegraph Peak, and it took a lot of shots to actually hit it. So we were able to, in order for us to observe it. All right, moving on. A big part of this is actually comparing these high silica sites, these sites with these obviously elevated silica, and we'll find some interesting changes in here. These are the ones with some real variation in values. High silica sites show variation in silica, titanium, aluminum, and iron. And then so this Greenhorn and Lubango are both in the Stimson, the same as Big Sky and Okoruso. And there's just not much variation here in these baseline sites, but you start to see a lot of variation here in these high silica sites. So, all right, and then the last 4 sites, there's not a lot of variation in these last 4 sites in the Murray. And then down below, I have the number of points used to get these mean values. And so sometimes we have points that maybe the instrument response wasn't exactly what we wanted, or like I said, accuracy wasn't great. So usually, so that's the reason why you get some odd numbers throughout this. And then the sites at John Klein and Cumberland have much higher numbers of points because we were just there a lot longer. I think we were here at this location for months, and so it allows for a lot more data to be collected. And then some of these sites have very few because we were having some issues with the instrument at the time, so we were only able to collect a few points during that time. So moving on, looking at geochemical variation. So here I have John Klein and Cumberland, which were in the sheepbed mudstone, Winjana, and then down here are Pahrump Hills. So JK is John Klein, CB is Cumberland, and then just all the Winjana points are down here. There just really isn't much going on in Winjana. But what we do see is this anti-correlation between silica and calcium, except at Winjana. And this is really due just because of the points are basically divided on silicate sediments and on calcium sulfate veins, with there being some indication of mixing in the tailings and the dump piles. It's a little bit, you start seeing it a little bit more down here in Pahrump Hills. The interesting thing is we just didn't really sample any calcium sulfate veins in the drill hole wall or the surface at the Pahrump Hills sites, except for at Telegraph Peak, like I talked about previously. All right, so these are the last 4 sites. So OU is Odom, MB is Marimba, QU is Quaila, and then SB is Sabina. And once again, you have the same anti-correlation between silica and calcium. And this is really the best you're going to see this trend. So, and this is present throughout pretty much everything. with the tailings in the dump piles representing a mixture of silicate sediments and calcium sulfates. Also, some work by some of Horton's other students have found calcium sulfate cements in this location, and with this variation seen both in the tailings and also on the surface in some of these sites, it's likely that there are at least some it's possible that there's some calcium sulfate cements at this location as well. So on. So Stimson, and this is really going to be kind of the meat and potatoes of this presentation. So first off, encircled here are the baseline sites. So you have Big Sky, Greenhorn, Lubango, which is LB, and Ocaruso for OK, with Greenhorn and Lubango being the high silica sites. And so the baseline sites have less variable less variable calcium, and the high silica sites also show this anti-correlation between silica and calcium, but it's definitely not as well defined as what you see here. So, and then another important thing is the baseline Stimson sites kind of plot on the line about here, and then the high silica sites are moved over this way. So it's not like they really would intersect. All right, so moving on to the Stimson drill sites. So the high silica Stimson sites are differentiated from the baseline sites by an enrichment in silica, which is why we call them the high silica sites, but also a reduction in most other elements. In this graph, we're using magnesium just because it makes a nice graph. So here we have the average values for the surface drill hole, tailings, and dump piles for the baseline sites. And by the way, this error bar is the standard deviation over the mean. And then over here, we have the same averages for the high silica Stimson sites. But what's important looking at this material is we go from the surface to the drill hole wall to the dump pile and the tailings in both sites, surface, drill hole wall, dump pile, and tailings. And this is showing a loss of silica with depth. Like I said, obviously the surface is on top. Then the drill hole wall is only the first centimeter and a half of the drill hole sampled. Then you have the tailings in the dump pile over here, suggesting a bit of a decrease. Now, the fact that the dump pile jumps back up in calcium, or sorry, the fact that the dump pile jumps back up in silica is a little concerning, but I think I have figured out why that might have occurred, and it should be a little bit later in the presentation. All right, so we wanted to check these results with the APXS results, and so we collected APXS data, or we went and asked the APXS team what their preferred data for these locations.
Hey, Ryan, you might explain that just a little bit. A lot of people are not experts on Curiosity.
All right, thank you. So APXS is a secondary, or not a secondary, is another geochemistry instrument on board the rover. Whereas ChemCam can do rapid remote analyses, so basically sample multiple targets in a day very, very quickly, but it has a very small laser footprint, which is kind of mitigated by taking rasters across rocks. The APXS is on the rover's arm. It has it's still a small footprint, but it's a much larger footprint than ChemCam, and typically it stays over a target for a while, up to overnight, up to staying there all night. The other thing too is APXS has been on rovers from Sojourner through ChemCam, so so those two and the Spirit and Opportunity rovers. So it provides an ability to kind of check with previous previous locations on Mars. So we went and looked, and the exciting thing is they see a decrease in silica from the tailings to the dump pile of both Greenhorn and Lubango. Unfortunately, their surface values are lower, and in this case much lower than the tailings. And but the one thing we already knew was that dust contamination on the surface of these sites can lower reported silica values. Unfortunately, this research that we're looking at was unable to provide a corrected value for location at these sites for several reasons. And so we attempted a very rough correction using a deconvolution calculation. And just in the interest of time, I'm going to skip over this one real quick. And so using a dust corrected calculation, we see at Greenhorn a higher silica value on the surface in the tailings, but not so at Lubango. However, in the Stimson, this high silica alteration occurs at these fractures and dissipates pretty quickly away from it. And so our Lubango drill site is right here, much closer to the fracture than the Lubango APXS value. So we'd actually expect them to have a lower silica amount as well.
Right.
And so,
yeah, just another, just to make it a little clearer, the problem is that if there's dust contaminating the surface, the dust has a lower concentration of silica, and so it will drag down the abundance. Is that correct?
right, yeah, yes, that's the problem. And there's not, so the Spirit and Opportunity rovers brought a brush along, or they brought a dust removal tool, a little grinder that got clean surfaces, and we don't have the same tool on Curiosity, so the ability to remove dust is a little diminished.
You can see that in your image very nicely, the coating of dust.
Yes.
So that's worth pointing out.
Right. So
partly clean.
yeah, so ChemCam, because of that ability to blast away fine material, actually does a decent job cleaning surfaces. So you can see the ChemCam rasters right here. I think there's one right here and another one right here. But then where APXS measured, you can't, it's not that clean. There is a difference in, these weren't all done on the same day, so it's not like a perfect comparison, but it does show kind of how much dust there was on these sites. All right, so real quick, I just want to touch on Buckskin before moving on. In ChemCam data, we do see a bit of a decrease in silica, like at the Stimson sites, but we also see a negative correlation between silica and magnesium. There's not a lot of calcium in the tailings, suggesting not a lot of the veins within the drill hole. The ChemCam and APXS data don't match great at this location, with APXS seeing an increase in silica and a decrease in magnesium with depth. Once again, there's always some trouble comparing the two instruments. They're both different analytical methods. They have different footprints. There's just there's always a lot of variation. But while we see some variation at Buckskin, we don't see a Stimson-like silica gradient, and we're really going to dive into this silica gradient here in a moment. And just remember, Buckskin is probably not a good example of this. So we're just really going to talk about Greenhorn and Lubango moving forward. All right. So ChemCam data shows shows a gradient from the surface to the drill hole wall to the tailings, and the APXS dust corrected values are not, I'm gonna say, are not inconsistent with this. Lubango's a problem, but there's problems with the way it was analyzed. It'd be great if we had like 6 more drill sites to really nail this in, but unfortunately we don't. And then APXS data shows a gradient from tailings to the dump pile. And in the drill finds, there might actually be a bit of a bias towards higher silica in these drill finds, which could be part of the reason why the dump pile ended up having higher silica in the ChemCam data. And this is based off of some ongoing research, or hopefully about to be published research, looking at alteration coatings on loose material and the ChemCam observation of that. So this suggests that there's a decreasing silica gradient from the surface to at least 3 centimeters. We're thinking at least 3 centimeters deep in the drill hole. Right. So I guess, so really the question that kind of popped into my mind was, could this gradient be produced by groundwater moving to the surface? This has to be a relatively recent event because the surface is undergoing deflation. And so we asked ourselves, when was the last time we could conceive of groundwater maybe being active at Gale? And so looking at some of the results, or some previous research, see that Mars has these extreme obliquity cycles to the point of pole ice actually it's thought can actually move all the way towards the equator, and Gale Crater is actually close to the equator. And so this last occurred 2.3 to 0.4 million years ago. And so if we look at kind of average deflation rate for flat surfaces over that time period, we only see up to 3.5 millimeters of erosion occurring, suggesting that the surface has been preserved since then. So next one. So the thought is equatorial ice could provide water that might recharge a small amount of groundwater, and then allowing for cycles of recharge and evaporation. This could dissolve silica lower in the sediments, bring it to the surface, and then the silica would precipitate most likely due to cooling, and then water would eventually be lost due to evaporation. And we think this occurrence might be we think this might be a local occurrence due to the high abundance of amorphous silica at this site. So this is kind of, this is all, we only have so much data on this. We can't say anything definitively, but if we're going to have this interpretation, there's the question of how much water would this actually require? And so first off, we know there's other places where you have increased silica due to the presence of water, and enrichment of silica in terrestrial areas due creating silcretes, which enriches both silica and titanium, like we see here. We don't really know what the climate function is at those sites for the formation of silcretes, but the present climates are typically dry, like Australia, and there's even some examples in New Mexico. And then also, there's already been previous work in this location invoking cycles of wetting and drying for the origin of these large crack features in the general group that Stimson's a part of. So continuing down, all right, so I did some geochemical modeling to try to get an idea of what's going on here. So for the mineral assemblage, we used the end result. We used the average mineralogy of Greenhorn and Lubango, and we assumed the amorphous silica content was equal to the total silica content within the amorphous component. And then for total mineralogy, we excluded the rest of the amorphous component. I didn't show this here, but the amorphous component is better than half at both these sites. And then for our starting composition, we kept the proportion of all the minerals the same. So we didn't really change anything except for amorphous silica, which we decreased so that the starting material only had about 50% 50 weight percent silica, and then renormalize the mineralogy to 100%. Basically, what we're trying to do here is limit this to a very late stage diagenetic event, at least in the original, in this first attempt at the hypothesis, just mobilize silica. We know that another diagenetic event happened to move the Stimson from the baseline material to this high silica material, but then we think this higher silica at the surface might have occurred a little bit later. We ran this using Freak-C. We ran experiments with water starting at 25, 15, 10, and 5 degrees Celsius. And then we ran the water, and then we cooled the water to 0 degrees Celsius. Like I said, we don't really have a great handle on all the possibilities here. So we're just kind of wanted to be able to run something where we could run some really cold water, which is what we're kind of expecting. And so basically the importance here is the difference in the silica dissolved at each of these sites. So you can see the change with a higher temperature dissolving more silica, having more silica dissolved in it than the in temperature water. And then as we cool down, we get less and less silica dissolved in the water. That means we need more and more water. And so, 1 second, moving on. I changed that already. So we filled a pore volume of material that of 1 cubic centimeter volume with water from these starting temperatures. We then cooled it to 0 degrees Celsius and calculated the amount of silica that precipitated. And we just ran this over and over again until we got to the end result silica abundance. And then we added together each pore volume to figure out how much water was needed. And so for each of these cubic centimeters, at 25, we need about 30 milliliters of water down to about 175 milliliters of water pure cubic centimeter if the starting temperature started at 5. And then this graph here just shows these same numbers graphically. All right. So is this a reasonable amount of water? That's a huge question. And honestly, milliliters per cubic centimeter is not something I really had a good mind for. So I wanted to, so we tried to get a better idea. Unfortunately, we've only sampled really material along the rover traverse, and that's only on that side of the mountain. So we don't know exactly how much material we really need to look at. So, so we decided to try to calculate the total amount of water per cubic centimeter necessary for this. And so for this calculation, we ran a bunch of calculations, assuming a distribution of high silica halos between 1 and 7.5%. So those halos break through through the Stimson, but they don't occur all that often. And we're assuming only the top centimeter of material is altered for this. And so using our highest estimate, which assumes 7.5% of the Stimson is covered in these high silica halos, and the original water equilibrated with silica at 5 degrees Celsius, it produced 1.31 times 10 to the 8 liters of water per cubic or per square kilometer for this to be for this to occur. We ended up with about a magnitude less on average of water necessary. But I think the really important thing here is if we use this highest estimate and say this occurred in only 1,000 Earth years, we get an average flow rate of 0.25 liters per minute for each of these kilometers. And we're not looking at like 100 kilometers. It's 5, 10, 15 kilometers. And probably we don't, like I said, we don't have a great grasp on it. But this is incredibly low when we compare it to glacial fed springs on Earth. Still trying to look for a good analog to this amount, but this is very, very little water flowing. So this really wouldn't require a lot of water, and it doesn't require a lot of time. First, these baseline drill sites, everything that's not the high silica Stimson and Buckskin are basically geochemically homogeneous down the whole 6.5 centimeter depth, barring some variation in the distribution of these calcium sulfate veins. The high silica Stimson sites likely have a decreasing silica gradient with depth. Buckskin does not have this. Buckskin has variation, but not the same gradient. It's probably just due to I'm not exactly positive. We don't have as many points on there as I would hope. So it's
Well, Buckskin is Murray formation.
Right.
It's a different deal.
Yeah, it's different formation. There's a lot of different things there, so it's just not the same thing. This gradient could have been caused by relatively recent groundwater flow from on top of Mount Sharp that flowed down, came up to the surface. It would have remobilized some silica and enriched the very top bit of the surface in silica. This might be somewhat analogous to terrestrial silcretes. The silica abundance is lower, so this ends up around 70 in the 70% silica. Terrestrial silcretes are up around 90, but it still might be maybe a somewhat analogous process, or at least a somewhat analogous phenomenon. And this probably would have occurred at periods of high margin of liquidity. Okay. If there are any questions, I'd be happy to answer them. Thank you.
So Ryan, how did the water get there? Do you think it was snowing and then the snow melted, or was it rainfall on Mount Sharp?
So
what do you think was most likely?
I don't know exactly how the precipitation or how the water got there, and I've read the papers about the Martian obliquity causing the polar ice to move, but it's never been really clear to me how that happened. And so I think probably what we're looking at, it might be this occurring at maybe like a transition period between transition period either towards high obliquity or away from high obliquity, where either the ice on the equator is building up or decreasing. But you know, these specific processes with the ice have not been studied, and so I'm not really clear on how that exactly happened. It's just kind of a hunch, I guess, on that.
You probably ought to also, you know, even though we don't think this happened, this had to have happened really recently. So actually, this is something you could maybe even mention, that people have called upon large impacts to change the climate. We may be calling on that for the Peace Vallis fan stuff, but this is so recent that it's not likely to be effective of a large impact.
Right. Yeah.
It might be worth mentioning.
I have a question about the amorphous silica.
Okay.
Where did it all come from? I mean, you've got up to 50% amorphous silica. What is the source of that?
There are, even within the team, there are kind of at least two thoughts on that. One group proposes geothermal waters moving up and depositing that. We have, so one of the things at Buckskin, one sec, I'm going to move up. Sorry. So over here at Buckskin, some of the, we have this huge amount of crystalline silica. So there's some idea that maybe, or earlier stage of water, maybe mobilize this or something else nearby, and moved it through the Stimson. Basically, just a large amount of aqueous alteration.
So whether it's amorphous or crystalline, it's probably coming from hydrothermal waters. Is the consensus, is that right?
So I think at this point, honestly, I've gotten a little lost on the origin of the buckskin because it seems to go back and forth. I think it had high amounts of tritomite in it, and there were some calls originally as like a silicic ash deposit. It's I don't really think geothermal water. This stuff occurred fairly late, especially like the Stimson was laid down fairly late in the history of Mount Sharp. So
I
I'm
think
not
you
sure
could just say it was very controversial.
yeah, it's very
happened
controversial.
there, but you're absolutely right that the difficulty is it has to have happened very recently, this mobilization, and so it's unlikely to be geothermal.
But the original high silica is thought to, at least by some, to be this layer of tritomite that was a volcanic ash layer that then was moved down into the lake and became sediments. But there's been discussion about that because some people really don't like that idea. They have trouble with tritomite being produced on Mars because of the evolved magma that would be needed for that. So they're trying to do make a lot of tritomite through some low temperature process. But personally, I think that a volcanic ash and a layer of high silica was probably laid down, and then you mobilized it from there.
We have a giant volcano, the Elysium volcano, to the north, so that's certainly consistent with that idea. But what Roger was alluding to also is that some people are blaming it on changes to the lake chemistry that could have led to a higher silica deposition in the lake sediments that was then utilized. So, yeah.
Another question related to this is, on Earth, when you get fine-grained silica deposited, it's usually microcrystalline, it's not amorphous. Why is it amorphous so much of the time on Mars and not microcrystalline?
So really, it's I don't think the XRD instrument on the rover can really differentiate between microcrystalline and true amorphous. It's kind of difficult to run those experiments on Mars to get the same amount. There's been a lot of work done on it, and they seem to the team seems to have settled more on amorphous, I think, at least for the majority of the silica. But I think probably the reason varies from site to site. And also, this is an amorphous component, so it's the chunk of the XRD spectra that the instrument can't match anything to, and doesn't have well-defined peaks. So there's a degree of we can't really figure out exactly what's in there. So assuming all the silica at the two Stimson sites were amorphous silica, were really just a way of moving the experiment along. There's only there's only so much we can know about that material right now, and so I needed a way to be able to do the experiments.
So you're saying it could be microcrystalline, you just can't tell that yet.
Yeah, I'm not a XRD expert, and these guys, their papers can be fairly dense at times. So I wouldn't really want to speak for that team at all. Just kind of reporting what they said.
Well, what I was curious about is there any reason the silica should be mainly amorphous on Mars and mainly microcrystalline on Earth?
Not that I'm aware of, and really this could come down to just the difficulty, between having a nice, well-stocked XRD lab and having an XRD instrument the size of a large briefcase on another planet. It's just sometimes you just hit difficulties that you can't really overcome.
Ryan, I think they're very, this has been seen for so long. I don't think there's any doubt that a large fraction of the material is amorphous, but the answer is nobody. Nobody has a great answer. People have suggested things like there's a lot of glass, volcanic glass, for example, that might have been be present as an amorphous component or other. But it's the large fraction of amorphous material is basically still quite mysterious, I think. It seems to be real. Any other questions? Ryan's making furiously sorting out these things, and we'll be in a month or about 2 months. We'll be doing his. We'll be revisiting this for his PhD defense. So you can all, if you're interested, he'll be doing this a little more, doing this again with a. Where everyone can see. Now let's see, there was something in the chat here. Let's see, okay.
Oh, I just sent you something.
You have to leave.
Yeah, I'm not in a rush. So just if you wanted to talk after this, I wanted to let you know I would have to.
Yes, and Ryan, I made some notes also for Roger's. I'll copy Roger as well, so we can. I think you can add a few. You've been giving this talk to the experts on the team. And I think there's some additions you can make to make it a little easier for the people who are not as familiar with the mission, to make it a little clearer. So I'll send that to you in a second, and copy Roger. So if he wants to add any other suggestions about the presentation.
Thanks.
Okay, thanks everybody. We're having fun with the rover, doing remote operations. Just some news on the rover. We've been stuck in one spot, not actually stuck, but doing multiple drills, and we did the most sophisticated organic analysis experiment that apparently ran successfully, but my guess is if they found anything interesting, it'll be months before you hear about it, because they'll be writing an embargoed paper for Science. So on the other thing that's exciting about what we're doing, though, is we're probably going to do we're in an area that has high manganese and manganese nodules, and so the groups led by the people up at Los Alamos, especially Patrick Gazda and Nina Lanza, have been pushing to do a specific a drill to attempt to get some of these manganese nodules material into the APXS, into ChemIn, to get the X-ray, as well as the SAM experiment to get the release material to identify the mineralogical nature of the manganese, which is a terrific, what could tell us a lot about lot more about the environment. Could even help maybe us understand some of the silica stuff. So a lot of exciting things going on. And so, and after we finish this, we'll be heading off to get up to the next major unit that we had seen that helped us select this site, which is the sulfate unit, stratigraphically higher up from where we are now. So meanwhile, Perseverance is on its way to Mars, and Roger's got his hands full with the SuperCam preparations, as well as the keeping Curiosity going and ChemCam. So we're glad to have you guys all look at us, and I guess that's all for right now.